Okay, so we're going to be looking at variance that we've got here, and you'll see I've got these two different distributions drawn, and it's about the IQs, which is one way of measuring intelligence between two different classes. So I have class X and class Y. And you can see here that the estimated mean is going to be the same for these two classes. And the reason that the estimated mean is going to be the same for these two classes is pretty clearly we can see that both of these distributions are symmetrical. They're gonna, if we're doing an estimated mean, they're symmetrical about this middle point that we've got here. So it looks like they're both gonna have an estimated mean of roughly 115. I've also got here that the estimated range is the same for the two classes. Now, remember the range is the top, the highest value take away the lowest value. And both of these graphs are going between 90 and 140. Now, obviously there's a grouped data, which is why I've used the phrase estimated for both the mean and the range here. But what I've got here is that the overall spread of the values is different for the two classes. So for class Y, which is the second one I've got here, the data is more spread out. And what I mean by being more spread out is that the results vary more. You've got lots of students getting all different kinds of IQs in this range here. Now, it is less spread for class X. And the reason I'm saying that it's less spread, because you'll still see like, okay, but look, this is going from 90 to 140, and so is this one. What I mean by it being less spread is that in class X, lots of students have got similar IQs. And I'm talking about these students inside this 110 to 120 group. So it's less varied, because if you imagine taking like a sample of these classes, you're much more likely in class X for them to all be closer together than you are in class Y, just because of the shape of that distribution. So what I've said is that the interquartile range would convey some of this information. You would have a smaller interquartile range for this class than you would do for this one because it is less varied. And it's more spread out. Sorry, it's less spread out in this one. But we do want to have a measure, a method, sorry, to measure spread that takes into account all of the values, even the extremes. We don't just want to do range. We don't want to do interquartile range. We want one where every single value in the distribution will contribute to that measure. And this measure that we're going to go for is called the variance. And it's also then going to lead us to something that you may have heard of called the standard deviation. So let's have a look at this. Variance is a measure of spread that takes all values into account. Variance, by definition, is the average squared distance from the mean. Okay, let's see if we can break this down what it means, the average squared distance from the mean. We'll have a look at this in just a second. We're going to concentrate on this pink box that we've got over here. So when I'm saying the average squared distance from the mean, this is what we're trying to build up to. First of all, we're talking about the distance from the mean. Well, remember what this x represents up here. X is our value that we've got. And if we subtract the mean from it, that would be how far away it is from the mean. And then we're going to square that distance from the mean. And we're going to add all of them together to find this average squared distance from the mean. We know that the average squared distance from the mean is adding up all of those squared distances and dividing it by how many that there are. Now, the reason that we do this squaring part that we've got in here is to make sure that the values are positive, because if you were going to be doing x minus x bar, obviously you're going to get some negative values. So part of the reason that this squaring takes place is to get rid of any of those negative values. Now, on a side note, because this does come up in some questions, there's this summary statistic, which is SXX, sum XX. What this literally means is it means the numerator of this. It means the sum of the squares of the x values take away x bar. And the formula for the variance, which is using this symbol that we've got here, sigma squared, can then therefore be rewritten as SXX over n. The reason I mention this is because there will be some questions that just give you SXX. They don't give you any other information. So you may need to just find out the variance by doing SXX divided by n, and that will come up in a question that we've got later on. This symbol that we've got here, this is sigma squared. Okay, sigma squared is the symbol that we use for the variance. Sigma by itself, not squared, is going to be something that is just called the standard deviation. And we'll be exploring that a little bit more on the next slide. So we don't actually need to know this full formula. We don't need to use this because it's quite a lot of work in that. You'd have to do a lot of subtracting, a lot of squaring, adding up, dividing it by how many there are. And so there is actually a much simpler formula for the variance and for the standard deviation. So there's the proof that we've got here, which is taking the original formula that's on that previous slide and coming up with this formula that we've got here. I'm happy for you to have a read through this. I think if you're doing further maths and you're really familiar with sigma notation, you should be able to be able to do this proof. It's not in the syllabus, but it's definitely worth reading through if that's the kind of thing that interests you. So for the variance, the formula we've just seen from the previous slide can be rewritten as sigma squared equals the sum of the x squareds divided by how many there are minus the square of the mean. And what I've written here is that we can translate this into something that's nice and easy to remember. The mean of the squares minus the square of the mean. So the mean of the squares means you're going to square your original values and divide it by how many there are. And you're going to subtract, you're going to minus the square of the mean value that you have also calculated. And the way we can remember this is MSMSM. In other words, the mean of the square minus the square of the mean. That's the way round that we would have this, okay? Little side note that I've written at the top here is that the sum of x squared does not mean the sum of x all squared, and you'll see that when we do that with some examples in just a second. Now, the formula for the standard deviation is whatever it is for the variance that we've got here, and you just square root it. And that's because of what I mentioned before, that sigma squared is for the variance and sigma is for the standard deviation. So this bit I've got at the bottom here is pretty important. So what we were working out in this previous bit that we've got here, right? We were saying what is the average squared distance from the mean? So for the standard deviation, when we square root all of this, what we're roughly finding is the average distance from the mean. Doesn't exactly mean that because the squaring and the square rooting doesn't completely keep it in that way. But what I've written is that the standard deviation can roughly be thought of as the average distance from the mean. So this means a couple of things here. If you add in a value to your data set, that is within one standard deviation of the mean, the standard deviation will, what do you think, increase or decrease? It's going to decrease. And I'm going to put in brackets and vice versa. So if you think about why this is true, if it's saying that the standard deviation is the average distance from the mean, if you add in something that is smaller than that average distance from the mean, and so it's close to the mean, then overall that average distance from the mean is going to decrease. So the important bit from here is that if the thing you add into your data set is within one standard deviation of the mean, in other words, if it's x bar plus or minus the standard deviation, then the standard deviation should decrease, and vice versa. If you added in something that was further away than that standard deviation, then the standard deviation is going to increase. So I am going to now do a couple of examples, and I will do these in this video because this is pretty straightforward here. So we're going to find the variance and the standard deviation. I'm going to do this one without the calculator, and then I'll do it with the calculator. So I've got the formula for the variance over here. It's the mean of the squares minus the square of the means. So the first thing I'm going to do is I'm going to find the mean of the square values. So here are my x values that I've got here. My square values are just going to be 3 squared and 11 squared. So I've got 9 and 121. So the variance for this data set is going to be the mean of the squares. So I'm going to add up the square values and divide it by how many there are. And then I'm going to subtract the mean value. Well, let's just quickly find out the mean value. The mean value is going to be 3 plus 11 divided by 2. So that's 7. So I'm going to subtract 7 squared. So what I've got is 130 divided by 2 minus 7 squared is going to be the variance. So 130 divided by 2 minus 7 squared. So I've got that the variance in this case is 16, which means that the standard deviation is the square root of the variance, which is just going to be equal to 4. I'm just going to quickly show you how you can find this on a calculator. Obviously, with these values, it's going to be quite a bit easier to do like this. I'm just going to put it on my stats version. Just going to go to the camera. Okay, so on the calculator that I've got here, just going to do this so it doesn't go off. I'm going to go to stats mode. I'm actually already in stats mode, but if you can't remember how to do that, you scroll along to number 6 that we've got here. I'm going to say it's one variable calculus. You should have the frequency thing on. If you haven't, you can just do that in the settings. So the numbers we just had were 3 and 11. And then you go to options. You then do the one variable calculations, which is number 3. And then you can gather all of those different values that you needed. So there was the sum of x squared, which was 130. We can find the average, which was 7. And actually, it tells you in the question here that this sigma squared x is 16, and therefore the standard deviation of x is 4. So we've got that nice and easy to be able to try. Okay, the next question, I'm going to do it with the calculator first, and then we'll do it manually. In fact, I think this one we will put them straight into the calculator. So we've got 2, 3, 3, 5, and 7. So I'm going to go back to my calculator, 2, 3, 5, and 7. And there were 2 of the 3s. So I'm going to actually just change the frequency for this one here. I'm going to just change it to 2. So what you can then get is all of the different values that you need from the calculations. So when we do my one variable calculations, we can see that the answer is going to be, for the variance, it's going to be 3.2. I've got the sum of x squared is 96. I've got the sum of x is 20. X bar is 4. So I'm going to take this calculator to one side, and we're going to do the calculations now on here. Okay, so let's go in using this formula that I've got at the top. So the variance is going to be equal to the sum of x squared. My calculator says that's 96. That's found by adding up 2 squared, 3 squared, 3 squared, etc. And it wants us to divide that by how many there are. My calculator's also got that for me, or I could just count them. And I'm going to subtract the average squared. So the average value for my calculator is 4. So I'm going to have it like this, okay? Let's do 96 divided by 5 minus 4 squared. So we get 3.2. Now the calculator actually shows me that it's 3.2 for the variance. And then I can do the square root of that 3.2, which is 1.79. And that's to 2 decimal places. Now the units for the sigma is going to be centimeters. Okay, for standard deviation, it is saying that on average, they are 1.79 centimeters away from the mean. Okay, that's roughly what we're trying to say in this version that we've got here. And we can actually extend this to frequency and grouped frequency tables. What I've said here is that it's better to try and memorize the MSM, the mean of the squares minus the square of the means, than the actual formula itself, because you'll just understand a bit better what's going on rather than trying to memorize a formula that looks like this. And I've said in an exam, you will pretty much certainly be asked to find the standard deviation for grouped data and not for listed data. Another little side note that I've got over here as well, just like earlier on, the sum of x squared is not equal to the sum of x squared. The sum of fx squared is not equal to the sum of f of x all squared. So what we're going to do here is we are going to, for this particular question, we are going to try and find out what the mean and the standard deviation is for this particular one. Now they've told us something that I don't know if they will always give you. They've told us this information that we've got running along here. I'm going to try and do it with the calculator to see if that's going to work better. So for my calculator, I'm going to put in the midpoints for these yields that I've got down here. So I'm very quickly going to put in 2.5, 7.5, 12.5, 50, 17.5, and 25. 20, oh, careful, that last one is going to be, I think I've made a couple of mistakes there. Number 4, the midpoint is going to be 20, and the last one is going to be 30. So I'm now just going to fill in the frequencies as well. So we've got 16, 24, 14, 12, and 4. Silly me, they'd even told me the midpoints. Now, I'm just going to show you how you can do this on the calculator to grab those different values that they've got there. So when you've got them all typed into the table like this, what you can do is you just go to the calculator, you go to your option, one variable calculator, and we've got all of these different values. Now they don't have the F in here because it's just doing it straight from the table. So we've got these different summary statistics. We've got the sum of x and we've got the sum of x squared. That's like the sum of f of x and the sum of f of x squared. So that's 755 and 12,037.5, which is exactly the two values that we've got here and here. So if they don't give them to you, you can use it in your calculator. Let's actually finish this question off then by doing the calculation. So the first thing it wants us to do is to find out the mean. Now we know that the mean is going to be the sum of f of x divided by how many there are. They've already told us that the sum of f of x is 755, and the total is that there are 70 plants here. So 755 divided by 70 is going to be 10.7857. So let's just do that as 10.79, and that's to 2 decimal places, and that's in kilograms. They also want us to find out the standard deviation. So the standard deviation is going to be the square root of the sum of f of x squared, so that's the mean of the squared, divided by the square of the mean, like this. So the actual calculation that we're going to be doing is going to be 12,037.5 divided by 70, minus the 10.79 squared that we've just worked out. Now actually my calculator is going to have done all of that. If I just scroll down, you can see on the calculator, if you've got it in front of you, that this is going to be 7.46 kilograms, and that's to 2 decimal places. So although you can go straight to the answer, it's always worth writing out this line here to get the method mark in case you've typed something wrong in your table. So let's have a look at one more of these. This time it says, the following table summarizes the times in T minutes to the nearest minute recorded for a group of students to complete an exam. So we need to be inputting this really carefully, and we need to think about what the midpoints are going to be. Now remember what I said before, these aren't the true class limits. So this one is actually going to be going from 10.5 to 20.5. But because you are subtracting a 0.5 and adding a 0.5, the midpoint of these two numbers is going to be the same as just the midpoint of these two numbers. So we can do the midpoint in the usual way, just by adding and dividing. So I'll do my 11 plus 20, and I'll divide it by 2, so the midpoint is 15.5. And then for the next one, the midpoint is a 21 and a 25, so the midpoint is 23. Then we've got 26 and 30, whoops, so the midpoint is 28. And then we've got 31 and 35, so the midpoint is 33. And then we've got 36 and 45, so the midpoint is 40.5. And then for the last one, we've got 46 and 60, so the midpoint is 53. Now they've told us some of this information down here, but let's imagine that they didn't. We would be able to do this all on our calculator. So I'm super quickly going to type in the data. So I'm going to just put in 15.5, 23, 28, 33, and 40.5 and 53, and then I'll fill in the frequencies as well. So I have 62, 88, 16, 13, 11, and 10. And now I'll just show you what this looks like on my camera. So I filled in the data into the table with all of the frequencies. They want the mean and the standard deviation. So I'm going to go to my options. I'm going to do the one variable calculations. And I can just go straight. Here's the standard deviation is the 9.29, and I've got the mean is 24.1875. I'm probably going to write in an extra line to show how I get this standard deviation, just to get a method mark. But I've got all of the information there, so I can check to see that it's correct. So the mean. We know that the answer is going to be what I've got on my calculator, but it's the sum of x, which is 4837.5, divided by n. And the calculator can tell me that there are 200 here. And now I can just grab this from the calculator, which is 24.1875. Then I'm going to find out the standard deviation, which we know is going to be the sum of ft squared over n minus, I shouldn't have called it x bar, I should have called it t, minus t bar all squared. So again, I can just actually fill these numbers in. I've got the square root of 13,428.1, sorry, 134,281.25 divided by 200 minus 24.1875 all squared. Again, I don't actually even need to type this bit here in my calculator because I've already got that. I've already got the answer recorded in this summary statistics. So it's 9.29 minutes, and I'm going to do that to 2 decimal places. That's not even to 2 decimal places. I should have just said minutes. Okay, so I'm going to add in a little extra bit here. Let's say I add in another student and they took, let's say that they took 30 minutes to complete the exam. What happens to the mean? Well, if you're adding in 30 minutes and it's bigger than the mean, it's going to increase the mean because it's bigger than the mean. What happens to the standard deviation? Well, the standard deviation is 9, and 30 is less than 9 away from 24. So it is less than 1 standard deviation away from the mean. So because 30 is less than 1 standard deviation from the mean, it will decrease. Okay, so you have got a question here that I would like you to have a think about answering. This one you can't use the calculator at all. Have a go at doing this yourself. Pause the video and then we're going to do this one together and then you can try exercise 2E. Okay, so here it says that Sarah is investigating the variation in daily maximum gust T knots for Camborne in June and July 1987. She used the large data set to select a sample of size 20 from the June and July data for 1987. Sarah selected the first value using a random number from 1 to 4 and then selected every third value after that. So this type of sampling technique that Sarah is using is systematic sampling. Systematic sampling. From your knowledge of the large data set, explain why this process may not generate a sample of size 20. Well, from the large data set, we know that for the daily maximum gust, there is some missing data. So the reason why is there are some days with missing data. All that they want us to do now is to calculate the standard deviation using all of this information that we've got here. So the standard deviation is going to be the square root of the mean of the squares, so the sum of t squared over n, minus the square of the mean. So we need to find out the mean, and then we're going to square it like this. So this one we can't use the calculator to do the whole value that we've got. So we're going to do, for our calculation, 374 over 20 minus, oh, not 374, 7,600 over 20 minus 374 over 20, all squared. So let's do this on a calculator. We're going to have 7,600 divided by 20 minus 374 divided by 20, all squared. So the answer is that our standard deviation is 5.51, and it's knots, 5.51 knots to 2 decimal places. Let's see how we did on these by looking at the mark scheme. So we've got the systematic sample. There are gaps because the data was not recorded. That's what we said. And then the answer of 5.51 that we've got right here. Notice how they do like to see the method mark of what you're doing. Okay, so that should be enough to help you now on exercise 2E.